Hello everyone. Today, we are going to explore the perfect gatekeeper in signal processing, the ideal filter. The task is simple. It allows only signals of specific frequencies to pass through while firmly blocking all other frequencies. Next, we will study this topic through the following sections. First, let's take a look at the first part, the frequency response characteristics of ideal filters. According to their different passband rules, ideal filters are classified into 4 types. For a clear understanding, let us look at the frequency response diagrams of these 4 filters. Ideal low-pass filter passes only low-frequency signals, from 0 up to a certain cutoff frequency. For example, retaining the deep parts of the human voice. Ideal high-pass filter, the opposite of low-pass. It allows only high-frequency signals to pass, such as filtering out background noise while keeping the high tones of instruments. Ideal bandpass filter opens only a specific frequency range, such as an FM radio, like a precise frequency gate. Ideal bandstop filter specifically blocks a certain frequency range, for example, removing power line interference, like patching the signal. Next, let's look at the second part, the ideal low-pass filter. We will first learn the definition of an ideal low-pass filter. The ideal low-pass is the most commonly used type. We can see that 4 frequencies less than the cutoff frequency. Its frequency response function is a complex exponential. 4 frequencies greater than the cutoff frequency. It is 0 as shown in Formula 1. Its amplitude frequency and phase frequency characteristic curves are shown in Figure 1. We can see that within the effective frequency range of the signal, the amplitude is 1. Outside the effective range it is 0. The phase response within the effective range, passband, satisfies a linear relationship. We reveal the characteristics of the ideal low-pass filter through 2 types of test signals. First test, impulse signal, impulse response. When an instantaneous pulse such as the clap sound is input, the inverse Fourier transform, as in Formula 2, shows that the output is an extended waveform, resembling a sinc function curve, with the main lobe appearing later. Analyzing the impulse response, we find that the waveform is distorted. This is because the pulse signal contains infinite frequencies, while the filter passes only low frequencies. The high frequencies are cut off, causing deformation of the output. Waveform delay occurs because the main peak of the output arrives later than the input. The delay time is determined by the filter's phase characteristics. Fatal limitation. The output signal exists even before the input arrives. This violates the law of causality, proving that an ideal low-pass filter cannot be physically realized. The second type is our test of the step response of an ideal low-pass filter. The excitation is a step signal, that is, an input that jumps from 0 to 1. The output, however, rises slowly, like a ramp, and produces oscillations near the transition point, similar to ripples or jitter, as shown in the figure. We find, in the rise time, the output takes time to go from low to high, and the rise time is inversely proportional to the filter bandwidth. The wider the bandwidth, the faster the rise. The oscillation amplitude is fixed at 9% of the step height and cannot be eliminated regardless of the bandwidth. This phenomenon is known as the Gibbs phenomenon. The step response curve on the previous PPT page shows this typical phenomenon. It is like a mathematical fate. A step signal passing through an ideal filter will inevitably produce oscillations. 2 major flaws hidden behind the perfection of the ideal filter. Flaw 1. Physical impossibility. The law of causality requires that the output cannot occur before the input, but the ideal low-pass responds before the input arrives. Solution. In practical engineering, use realizable filters, such as the Butterworth filter, to approximate the ideal characteristics, accepting small passband ripple in exchange for causality. Flaw 2. The eternal contradiction between distortion and bandwidth. Bandwidth matching principle. If the filter's bandwidth covers the signal's bandwidth, for example, speech through a wideband low pass, the output is basically distortionless. If the filter's bandwidth is too narrow, for example, music through a narrowband low pass, high-frequency details are lost and the sound becomes muffled. Today we will solve a specific example problem, understanding how an ideal low-pass selects signals. First of all, we need to break down the key steps of this problem. Step 1. Analyze the frequency components of the input signal. Given the nature of the input, it consists of two parts: the sampling function SA of t and the cosine function cosine of 2t. First, using the duality property of the Fourier transform, obtain the transform of SA of t, as in formula 1. Next, apply the frequency shift property of the Fourier transform to formula 1 to derive formula 2. Finally, obtain the system's output response, as in formula 3. Is the problem finished once we have the output in formula 3? Not yet. We can see that the cutoff frequency of the low-pass filter is still unknown. We need to determine the final output based on the size of the cutoff frequency. From the input and the filter's frequency response curve, figure 1, we see that different cutoff frequencies yield different results. When cutoff is greater than 3, all frequency components of the input pass through the system. The final result is as in formula 4. When cutoff is less than 1, none of the frequency components of the input pass through the system. The output is 0, as in formula 5. When cutoff is between 1 and 3, only the frequency components from 1 up to the cutoff frequency pass through the system. The result is as in formula 6. Today we explored the ideal filter in depth. First, we learned its 4 types of frequency response characteristics, which can precisely select different frequency signals. We focused on the ideal low-pass filter, and through impulse and step response tests, discovered its 2 major flaws: physical impossibility and the distortion, bandwidth trade-off. We also discussed practical countermeasures, using realizable filters to approximate ideal characteristics, and matching bandwidth to preserve fidelity. Finally, through an example problem, we mastered the method of analyzing signals with an ideal low-pass filter, and understood the need to determine the final output according to the cutoff frequency. I hope you will review this after class to deepen your understanding.